my talk is going to be about NASA's MAVEN mission to Mars, and specifically, I will try to answer at least part of the question related to why Mars looks the way that it does today and what happened to its atmosphere. So I hope everybody can hear me and everything else is functioning smoothly. So maybe one quick explanation before we begin. MAVEN here stands for Mars Atmosphere and Volatile Evolution. That's a name both of the mission and the spacecraft, and in retrospect, it's a somewhat strange choice of a name, but now we have to stick with it. And let us begin here. So, a brief outline of my talk. I will spend the first few minutes, or maybe the first 10 to 15 minutes, giving you a very brief introduction of Mars. Especially, I will try to focus on Mars's early history and on the pieces of the puzzle that we know so far, and also I'll be looking at to illustrate a little bit better the part about the climate evolution on Mars, which served as a motivation for launching the MAVEN mission in the first place. And after that, we will move on to the bulk of the talk, which will be about the MAVEN mission itself, and in particular about the science highlights. Now, there are too many interesting results coming from the mission to mention them all, but I'll try. I'll make a fair attempt to include them in whenever I'm presenting something. Finally, I will end the talk by discussing what can we learn about the very early history of Mars by taking the results that we obtained from MAVEN and putting them together with the other results obtained from other missions, as well as the last 50 years of Mars research. And what can we learn about the climate that might have existed about 3 or more billion years ago on Mars? And then I will briefly conclude. So let's go ahead. And as I mentioned, the central question that both the MAVEN mission and the rest of the scientific community interested in Mars research is trying to answer is whether Mars in its past, when it was young, looked more like the left part of the slide or the right part of the slide. Specifically, was there any liquid water flowing on Mars at some point in its history? Did we have perhaps oceans on Mars, or at least lakes and rivers? Was it periodically, or there was a long stretch of time which would be of particular interest to, let's say, astrobiology, or not? Or most of the time Mars just stayed this cold, very, very dry desert that we see today, because this is the best description of the modern time Mars. So I highlighted here specifically 2 reviews that I consider to cover the topic from a different perspective, and they're both excellent. One is by the PI of the Mars MAVEN mission, by Bruce Jakosky, and it's specifically focusing on atmospheric loss to space. The other, a little bit older review, addresses the problem of climate of early Mars, and for experts, something that is called the faint sun paradox. And it's both of them stand for a very interesting read. So let's start by looking at Mars, the basic facts, what we know about the planet. So if you compare it to our very Earth, the first thing that we can see is that Mars is about, it has diameter which is about half the size of Earth's. It has the surface gravity that corresponds to about 1/3 of that on Earth, and the mean distance from Sun is about 50% larger, which means that just based on that, we would already be able to expect certain things related to its atmosphere and evolution. However, things are usually not that simple when it comes to our understanding of planets, as we have learned first on the examples that we have here in the solar system, and then later on exoplanets. So the present-day atmosphere of Mars is mostly CO2. I'll try to get a pointer here. Yeah, this is some sort of a pointer. So it's mostly CO2. There's an admixture of nitrogen and actually a fairly significant amount of argon. This is something that experts would immediately notice as a parameter that stands out. However, the surface pressure on Mars is very low. It's only about 6 millibar, and that would amount to about 2% of pressure on top of Mount Everest here on Earth, which is not very significant air pressure. And another interesting thing to observe here is that the length of day on Mars is very comparable to that that we have here on Earth, which makes Mars one of the main candidates for future colonization. Now, at present, we also know that Mars is very cold. It's on average, the mean temperature at the equator is about -60 Celsius, and it gets as low as -120. So clearly, at those conditions, we cannot have liquid water. And another thing that makes it even more difficult, perhaps, for existence or for presence of life on Mars, is that because the atmosphere is not very dense, it doesn't offer sufficient UV protection, and in particular, it gives minimal protection from solar storms. Okay, so this is our starting point. Now, in addition to looking at Mars through a telescope, which most of us can do, because it was always perceived as sort of a twin planet to Earth, Mars has been a subject of very extensive scientific interest and research. And basically, from the 1960s up to now, so over the last 60 years, a number of robotic missions were launched to Mars. And they're illustrated here on this slide. So the blue lines correspond to the missions launched by the US. The Soviet Union are given in red, of course. And the post-Soviet Union, Russia, are the yellow ones. And there are a few missions launched by Japan and European Union, as well as more recently, one mission by India. And in 2020, which has been a particularly interesting year for Mars research, a total of 5 missions were planned, but 3 were launched, including one from China, one from the United States, and one from the UAE, which is the HOPE mission that Aisha mentioned in the very beginning. And there is also a logo of SpaceX here, indicating Elon Musk's very strong interest to build a Mars colony and to go there and die on Mars. I'm quoting his words. In any case, the very first mission that gave us high-resolution photos was one of the Vikings, and that was in 1976. And it resulted in this photo that you see here, which is basically 1/2 of Mars observed from a distance, and the second one, which happens to be one of the most shared photos of Mars that exist currently at the internet. And we can see several features in here from those 2 photos. The first one is that Mars looks very dry. We don't see any bodies of water. There's no blue. There's only a little bit of ice at the poles, and it is actually difficult to see in these photos. And the other feature that is immediately obvious is that there's lack of atmosphere. So there's a clear transition going from the planet itself to space. We don't see much of an atmosphere on Mars. It is very different than, for example, when we observe Earth or Venus. And the third thing to observe, of course, would be these geological features that are fairly impressive and at a much larger scale than what we're observing here on Earth. Now, going back a little bit to the models and theory that we know about the planet formation, this would be the first step that we try to rely on if we are trying to understand what happened with the early Mars's atmosphere. So we know that basically the planetary embryos formed very quickly. It took only several million years after the formation of the solar system, and after that, those embryos accreted and started creating bigger planetary objects. And when this process started, it took about we can estimate about 50 million years for the crust in the form as we know it here on Mars to form. And we get this information from extensive modeling and from isotope data. So I listed here a paper that gives a very, very nice recent summary of what is understood about it. Now, this is important because in geological scales, this is actually a very short time. And during that time, the early or primordial atmosphere of Mars was formed as well, and it happened through the degassing of the basically what was a magma ocean trapped inside the crust, and degassing occurred through the crust that was forming and produced the very early first atmosphere of Mars. And of course, such an atmosphere would have been very different than the one that we observe today. And the only clues that we can get about it comes from modeling and from this little information that we can extract based on the isotopes and the nuclear physics related to the isotope isotope transformation and chains of these processes. However, the crust of Mars, the surface, basically remains our window into early Mars, just because it was formed so quickly after the core of the planetary object itself was formed. So it holds many clues to the geophysics of early Mars, and especially those are easily present in terms of topography, in terms of geomorphology, and in terms of variations of gravity and magnetic fields. These are all the things that we can measure. Now, since my talk is mostly about the atmosphere, you may wonder, why am I even mentioning all this? However, for understanding the atmosphere of Mars, and especially the early atmosphere, it is impossible to completely separate it from the rest of the planet. All these processes, all these systems are sufficiently interconnected that it's not, if we try to just isolate one of them and talk about it, it's not going to give a full picture, and we might very easily make mistakes by describing one system correctly, but completely neglecting the others. So, as I mentioned, one of the interesting parts to explore is the magnetism of the planet itself. And for a long time, it was believed that Mars doesn't have a magnetic field, and it certainly doesn't have a magnetic field in the sense that Earth does. This strong global dipolar magnetic field. However, it was the Mars Global Surveyor mission, or the MGS, that discovered from orbit that there are traces of magnetism present on Mars, and they manifest as these little patches that are distributed over the different parts of the surface that exhibit very strong localized fields. And this was one of the main discoveries. One of the main discoveries of the MGS. We now believe that such magnetized material represents what is basically a crustal remnant of an extinct magnetic dynamo, and basically very clear piece of evidence that at one point a global scale magnetic field existed on Mars. But the models suggest that such a global magnetic field probably went extinct a long time ago, possibly about 3.5 billion years ago. Now, the other thing that we can learn from the surface is by basically examining many photos taken by the spacecraft. And many of these photos reveal some sort of traces or signatures of features. This would be purely from geological features or geomorphological that we believe might have been formed by flowing liquid water, or at least this is what the analogy that we can do to Earth can tell us. So, for example, this one in here, what we see here by examining the geomorphology is a signature of channels that have been carved by floods. And there would be another example of valley networks carved by rain. And finally, this one, the crater lake dam burst, is a fairly strong piece of evidence suggesting that at some point these craters were filled with water. Now, why water? Well, because it's if you look at chemistry, it becomes fairly difficult to come up with another liquid that could exist at physical conditions that are present at Mars. Now, another piece of evidence coming from the surface comes directly from the rovers. And in particular, rovers landed at different locations on Mars that were not randomly selected. Instead, that they were selected based on these orbital maps. And they were targeting different parts of the terrain where the scientists were hoping to find traces of minerals that would indicate presence of liquid water, or maybe even life, maybe fossils of bacteria. This is a long shot, of course. However, the presence of different minerals was definitely confirmed, and since I'm not really a geologist, I always hesitate to talk about minerals. But for example, mudstone was clearly found in Gale crater, and then there were these very characteristic features called blueberries that very much resemble some of the formations that are found in southern Utah. They were also confirmed, and a number of others. So one feature that all these minerals share is that none of them could exist without presence of water. It might be at least episodic rainfall, or in some cases it would basically require those parts of the surface to be submerged for a long period of time. So this gives us another strong hint that at some point, indeed, there were water flows and different features containing water present at Mars. Which of course brings us to the question, what happened to the water? Where did it go? Did it go up or did it go down? So up would be into space, to atmosphere and ultimately to space. And down would mean into rocks, and somehow those rocks would be circulated to end up deeper in the mantle. And of course, the other questions related to this, if there's really water, the question was how deep was the Martian ocean? And at what point did it exist? And how fast did it evaporate? And finally, what physical mechanisms are responsible for this? Why did this happen? And one thing that is, at this point, it seems to be easier to explore, at least given our limited time frame that we have at our disposal. It's the hypothesis that the volatiles went down. So these little dots here on the map of Mars illustrate the presence of different types of minerals, and all of these minerals require presence of water to be formed. So this was another major result coming from the observations by the MGS, and we can identify based on lots of images that we obtained. We can identify minerals such as phyllosilicates, such as silicas, chlorides, sulfates, and carbonates. And based on what we know from the Earth, we know that most of the CO2 that we have on Earth is actually stored in carbonates. So, of course, on Earth, only 0.04% of atmosphere is really CO2. And on Mars, if we project based on what we know, we can we can deduce that about 3 millibars of CO2 might be stored in the observed and extrapolated carbonates, which is interesting, but is definitely not sufficient to explain denser atmosphere that is required for liquid water flow to exist on Mars. Which means this is not the explanation that we are seeking. And that leaves us with the up direction. So the first information that we gathered, sort of a direct evidence of an escaping atmosphere on Mars, comes actually from X-ray. And there are images here taken by the Chandra Space Telescope in X-ray, and 2 years later, in 2003, by the XMM Newton. And those images show X-ray emissions coming from the entire surface of Mars. As well, XMM Newton had a higher resolution for particular wavelengths. So, especially the XMM Newton revealed that this kind of emissions extend further out from the Mars's disk. Those indicated, after the physical modeling was done, that there was actively escaping hydrogen present, and not only close to Mars, but also this is arc-second resolution, so it doesn't translate exactly to the units of length. But if I put the laser pointer in the middle, this roughly corresponds to the disk of Mars. So there will be thousands of kilometers around, or tens of thousands, of basically escaping hydrogen. So this was a clear observational evidence of hydrogen. Next, we fast forward to year, I believe, 2013 or early 2014, when the MAVEN spacecraft was approaching Mars. It took several snapshots of Mars from a greater distance than its later orbit during the scientific phase of the mission. And based on these images, it was possible to extract, again, the information about the atomic hydrogen escaping to space, its extended corona, and as well as the proof of oxygen and atomic carbon escaping to space, with the carbon corona being a little bit more diffuse and a little bit more ambiguous to explain. So this was, even before the scientific phase of the mission started, this was a very optimistic sign that something will come out of it. And the last part of the hypothesis that volatiles went up comes from the fact that many gases that we were able, whose concentration we were able to measure on the surface of Mars by the rovers, ended up being isotopically heavy, meaning that there was more of the heavier isotope. Like, for example, there was more of the 38th argon as compared to the 36th argon in relative terms on Mars than on Earth. And the similar findings, for example, for nitrogen, and especially for D/H ratio, which of course we can easily explain through thermal escape. All of this suggests that the atmosphere was thicker in the past. Now, let us move on to the bulk of the talk and discuss a little bit about MAVEN itself, and go through the science highlights of what we have learned so far, and then we will put things together and summarize. So all these things served as motivation to launch MAVEN, because as you know, it's not always easy to persuade the federal government to give you a few hundreds of millions of dollars to actually fund the mission. So probably the people doing the convincing were much better speakers and more eloquent than myself. So MAVEN itself, when it was built, looked like this. This is, of course, an artist impression because nobody took a photo of it in the orbit. And it had 3 suites of instruments. The first one in the yellow frame here was dedicated to tracking the solar activity. Then there was one in the red frame that was specifically designed to trace the ion-related properties and processes, because the assumption was that lots of ions were escaping from Mars. And then the final set of instruments was actually the most interesting one. And those are the IUVS, the ultraviolet spectrometer, and also the mass spectrometer for the neutrals, which were specifically designed for MAVEN and able to trace what is happening with the neutrals in situ as the MAVEN was doing its orbits around Mars. Now, another specific aspect of the MAVEN mission was the mission architecture itself. Here on this top right figure, in white is illustrated roughly one orbit of MAVEN. And you can see that the orbit in which MAVEN was inserted was a highly eccentric one, with the lowest point, so the periapsis of the orbit, being as low as 130 kilometers above the surface. And well, the highest point, or the apoapsis, being at about 7,000 kilometers. So this is very important because this specific eccentric orbit allowed MAVEN to both observe a good part of Mars from a distance, as well as actually pass very low and dip all the way into the ionosphere, and possibly as low as the homopoles, which would be the place where the mixing of the lower atmosphere and upper atmosphere starts taking place. The orbit was also designed to precess, according to this figurine here, over about 3 years of the main part of the science operations of the mission. Another aspect that is actually important to mention is that the mission took place during the low solar cycle. There should be only one solar in here, which means that majority of the results that we obtained come from a part when the solar activity was close to its minimum, or basically at its minimum. And this was both advantageous and disadvantageous. The good part of it was that there was less noise in the measurement. The bad part was that, well, we had less signal, because many atmospheric phenomena depend primarily on the UV and solar wind output from the sun. Now, this slide came from the mission planning phase of MAVEN, and it briefly summarized the groups of atmospheric escape mechanisms that are believed to be presently active at Mars. So let's try to explain them. They're grouped into the blue ones and the red ones. All of them are driven by either the EUV, the extreme ultraviolet radiation from the sun, or by the solar wind. So the blue ones are related to the neutrals. So the escape of the neutrals that primarily happens through so-called Jeans escape, which is applicable to the lightest atoms only, which is hydrogen, to some extent H2. And also the other very important mechanism is so-called photochemical escape, which I will explain in more detail. And the sputtered neutrals, due to the collisions with ions that get ionized through radiation as they escape and recollide with the Mars's atmosphere, was also named as a third candidate. And the processes in red are the ones related to the ions, and they come either from so-called pickup mechanism, when the stream of solar wind passes over Mars and just picks up electromagnetically the ions that are in its vicinity, or the local processes and recollisions can create fast ions and that escape in forms of ion outflows. This is a very general level description. So this is what we expected. Now, let me go very briefly to some of these processes. So the number one, the most important process for the current escape of Mars's atmosphere is so-called thermal or Jeans escape. And as I mentioned, it applies only to the lightest atoms, to H and to some extent to H2, but already for example, for deuterium, it's not the primary process. The reason for thermal escape is extremely simple. We simply look at the Maxwell-Boltzmann distribution, and we take the tail of the distribution above, that is going to be above the escape velocity for hydrogen, and we can say that all of these atoms that are faster than that can simply escape. Mars's gravity is not strong enough to stop them. So this is a big difference between Mars and Earth, because here the thermal escape of hydrogen occurs, but it doesn't occur nearly as significantly as on Mars. Here on the right, there is an image of the hydrogen corona, which was taken very early on in the mission. So with respect to hydrogen, one very important result that I chose not to specifically go over in here is that it was found that the hydrogen escape rate can change by as much as 1 order of magnitude, or even 20 times, over the Martian season. This was a completely new result coming from MAVEN measurements, because up to that point, it was believed that the thermal escape is more or less constant, that it's going to be simply this part of the distribution that keeps streaming out into space. This is an active area of research, and you can ask me questions about it later. And in fact, this is one of the topics that the EMM HOPE mission is capable of exploring further, and hopefully contributing something to the explanation of what is happening with the variation of the hydrogen escape. Now, the second very important part of or group of mechanisms are so-called photochemical escape mechanisms, and they happen because of the stored internal energy in molecules. So I will illustrate it here. And in particular, atomic oxygen escapes photochemically. So what happens is, we simplify Mars's atmosphere. We have O and CO2. We are left with only them. We add the sun. We photoionize CO2. There's an electron. CO2 plus and oxygen collides and forms O2 plus and CO. We would call this O2 plus to be formed through dissociative recombination of electrons and CO2. Now, alternative process here that can happen is the formation of O plus and CO2, and again, electrons will come from the photoionized oxygens, and they can collide with either O plus or CO2, and basically produce the same system again, either O2 plus or CO2. Now, O2 plus is the starting point. This is why it's in green, because those molecular ions will further recombine with 3 electrons to create 2 oxygens. And those 2 oxygens, when they're created in this kind of photochemical reaction, will have significant kinetic energy. So specifically, there'll be 4 major channels, and the 2 of them illustrated here in red, which constitute about 75%, will be able to, I mean, the oxygens formed in this way will have enough kinetic energy that they can directly escape to space if they are pointing in the right direction. And then what happens is let's say the top part, or the 1/2 of these oxygens that can escape due to the geometrical restraints into space will actually escape. The other half will just recollide with the atmosphere below. So this is currently the dominant oxygen escape mechanism from Mars, and it's only second to the thermal escape of hydrogen when one looks at rates. MAVEN indeed conducted measurements of oxygen escape through this mechanism and confirmed this process. This was also a very significant confirmation and confirmation of this mechanism. Now, the third class of processes are so-called ion escape processes, and they're mostly driven by the solar wind. So here on the left, we have a schematic representation of Earth with Earth's strong global magnetic field that looks like a dipole that is protecting us from solar wind, at least in the first approximation. On the other hand, this is an MHD simulation of what is happening with Mars's atmosphere, and especially with the boundary of the upper atmosphere that faces the solar wind, and it shows those orange lines which show the trajectories of the ions, with majority of them going up and then kind of behind Mars. So this was an early simulation, this particular result, before we had data from MAVEN. Now, MAVEN, since it was equipped with the suite of instruments designed specifically for characterization of ions, was actually able to measure far more precisely this kind of outflows of ions, and especially in case of oxygen plus, and confirmed this result in combination with modeling. So it was a synergy between modeling and ongoing measurements of ion outflows. And now we know that the ions are escaping from Mars roughly following this kind of chart here on the right. There's a big plume on top, and that was named for the press as the rock star Mars. Think of the hair. Now, I even have a little movie in here that I might show you. So I'm not sure how this is going to work, but we'll try. It shows basically the solar wind coming in and being deflected around the Martian local environment and the induced magnetosphere, and then forming this kind of escaping ion simulation. And then we observe how this behaves as the Mars turns around. But for the sake of time, I will end it here and jump to the next slide. This movie, by the way, I should give credit to NASA illustrators for making it. Finally, there is a fourth group of processes that are also important for the escape, and especially for the escape of heavier particles, and they would all be driven by the collisions with different superthermal atoms. So the subset of the Maxwell-Boltzmann distribution, which actually wouldn't follow Maxwellian distribution, would form another cusp of very hot atoms, and mostly they come from the photochemistry of either O2 plus, dissociatively recombining with electrons, or CO2 plus or CO plus, and as well as from the direct impact by very energetic solar wind ions that penetrate deep into the atmosphere. And one example of such a process would be the H2 escape that is driven directly by hot oxygen atoms. So in this case, H2 would escape directly as a molecule after being hit by an energetic oxygen, or it would actually react. This would be a very high temperature reaction, about effective 30 or 40,000 Kelvin, which is outside the domain of conventional chemistry. However, it can still form different molecules like the OH that, when formed, still possess enough energy to directly escape. So I'm also showing this slide because I'm doing here a little bit of self-promotion, because this particular class of processes is one of the focuses of my work. And because of that, I included another slide, and I named it for experts only. And there is a distribution in here of this H2 molecules, where on the y-axis I would give the rate of escape, and on the x-axis would give the rotational quantum number of them. In other words, it would show that for the photochemical escape, which is the red curve in here, we would have very, very different profile of these excited rotational states of hydrogen that are escaping. Then for the case when we have simple Jeans escape, which starts as much stronger in the beginning, but then rapidly falls off. Or if I try to illustrate it, so Jeans escape would do this, and escape due to the collisions would prefer to do this. And yeah, so this is an example for H2. However, it can happen to other molecules that are much heavier than H2, including water itself, which is a very interesting feature of this group of processes. Now, when we put everything together, we arrive to one of the most important results of the MAVEN mission. I would consider it to be the central finding, actually. And this was deduced from the ratio of argon 38 to argon 36. And it was basically an estimate of how much of the Mars's atmosphere has been lost to space so far. The idea here was to look at the amount of argon 36 and 38 at different altitudes. So we know we know its surface from the measurements by the rovers. We know the homopause, and we have the exobase. Homopause we don't know exactly, but we know approximately from MAVEN. And we could observe that the ratio increases with altitude, which would tell us that the loss from the top of the atmosphere prefers to remove lighter argon and leaves behind the argon 38. So based on that, the extrapolations were made, and it was suggested that about 65%, so 2/3 of the Mars's atmosphere basically escapes to space. The details are given in this science paper, which is a very interesting read, and probably our best estimate of how much of Mars's atmosphere was lost to space so far. Now, this will conclude our story when it comes to the present day Mars and the loss of the atmosphere. However, another and sort of a bigger objective of MAVEN mission was to find the total atmospheric loss over time. We could estimate something from argon. However, it doesn't really tell us the whole story, because when we are doing that, we are assuming that in the past Mars's atmosphere looked exactly like now, which is of course not the case. So to do this, to answer this very complicated question, one needs to look at the history of solar activity, at different events that happened over time, and look at both isotope ratios and apply different models that we know. And when we do this, unfortunately, we arrive at the answer that is still too simplistic. And such an answer would give us that about hundreds of millibars of atmosphere have been lost over Mars's history. So maybe 200, maybe 300. Some results show 350. And at that point, we are approaching the atmospheric density, which is large enough for the Mars to warm up sufficiently. Think of CO2 as being a very effective greenhouse gas. So to Mars to warm up sufficiently to actually start supporting at least the part of a year liquid water. Now, as I said, what we got there is still too simplistic. This is a short review of the main geological eras on Mars as we go back on time. And I'll just flash this slide here for 30 seconds. Basically, Mars is now in so-called Amazonia, and it stayed in this period for about 3 billion years. So nothing interesting was going on. However, before that, there were much more dramatic geological processes acting on Mars, and the effects of those processes are illustrated in here. I'm not going to go through them, but what I would like to say is that if we make a little table, so we have Amazonian, Hesperian, Noachian, and pre-Noachian, as we go back in time, we need to include more and more of these processes that we cannot see today, but that would still have very significant, or even the dominating impact on Mars's atmosphere and escape. And especially as we go back, we know less and less. So at first, we know that obliquity, eccentricity, solar EUV output, and solar wind are very important. But then as we go back, there's outgassing from the core. Then there are perhaps volcanoes. There are impacts, because in early history of solar system, the impacts were much bigger and more violent. And finally, there is the whole story about the global magnetic field on Mars, and when it was formed and when it ceased to exist, as well as the very early hydrodynamic escape, when the conditions were such that the entire atmosphere could actually flow out in space, almost like a liquid, like a steam coming out. Unfortunately, what we have described so far would fit only the very first column here, the Amazonian. Other things, other eras, as we move back, become more and more unknown, which adds to the difficulty, to the complexity of this problem. There is also some chemistry going on, which we are not completely certain about. Now, moving on to the conclusions of the talk, I think I'm still on time. Basically, the first conclusion is that the role of atmospheric escape in the climate evolution of Mars is actually a very complex problem to solve. We got a lot from the missions that we launched. We know now about Mars far more than what we knew 50 or 60 years ago when the first orbiters arrived there. But still, there are many pieces of the puzzle that are not fitting that well, let's put it that way. And the other conclusion is that we have now classified different classes of this escape processes based on their variability in time and space, based on how they overlap, and based on what are the prime drivers of them, what they depend on, such as the solar output or the seasons, or perhaps the chemistry and composition of the atmosphere. As we know more about these parts, we will be able to explain better and better what happened with Mars. So currently, what we believe is there were indeed at least episodic times on Mars when liquid water could exist. All of the evidence that we collected so far supports that. Now, an extra slide after the conclusions is this is what I took this morning, the screenshot. This is the journey of the EMM Hope, and we can see the red trajectory here, which is how far Hope actually traveled, and now it's approaching the last critical phase of the flight, I may say, when it has to conduct a complex maneuver, which requires firing the thrusters for about 30 minutes to slow down and enter Mars's orbit. So it is, I guess, the hope of the scientific community that the Hope mission will be able to provide extra information about two specific processes on Mars. One is the hydrogen escape and variability. The second one is oxygen escape. The third one that can be deduced indirectly will be about molecules. And we are trying to form here a small group of people that would actually specifically focus on the molecules. And this will be also a new finding and a very, very interesting one to put into the bigger puzzle. Now, usually I have to end this kind of talk with an attempt to answer the questions from the audience. Is it possible to terraform Mars? Can we live on Mars? And so on. So because of that, I usually include the little bonus topic, which is about terraforming Mars. Specifically, there was the movie, The Martian, which I believe most of us actually watched. And the question here would be how to terraform it, how to make the Martian atmosphere great again, or the MAGA. Because what we see here from this little animation on the right, taken from the movie, this would be the astronauts fighting the horrible dust storm on Mars. But as you know, this isn't real, because the densities, as I mentioned, about these 6 millibars, even if we have winds blowing at 300 miles per hour, I don't think we're going to feel anything. However, this may be real someday. And this is why I'm often asked this question. However, this is not going to be the topic of today's talk. And maybe sometime in the future, if there is time, I would be very happy to give a specific talk about the scientific and slightly less scientific ideas on how to terraform Mars. The point is, we can do it. However, we may need to look like this by the time that we have actually done it. So with that, I thank you for your attention.
All right, I think I'm back. I think everyone can hear me now. One moment. I'm just trying to stop the recording. If anyone has any questions, can you raise your hand? We only really have time for 2 questions. And it would be good if those questions, Dr. Yanis, unfortunately, are from graduate students. So I'll let Jalan speak, and in case nobody else answers, then Yanis, that would be, I'll allow you to ask your question. So Jalan, I'm going to unmute you. So go ahead and ask your question.
Well, thank you, Doctor, for this presentation. I'm sorry, I'm really not in this field, so I'm not expert, but I have a question. Can I conclude that because of the extinction of magnetic field, the atmosphere is lost on the Mars?
Well, this is a good question, but basically the answer